Hi everyone, in this video we will train our transformer model. I will explain the training process, share best practices, and show you how to avoid common mistakes that can stop your model from learning. This video has two parts. First, I will go through the slides and then we will train the model together. Training a neural network follows these steps. First, we use the tokenized data and split it into two parts, training and validation. From these, we create data loaders, which feed the model batches of data during training and evaluation. Next, we set the training parameters like the number of iterations, learning rate, and optimizer. We also save the model regularly, for example, every 100 iterations, and also don't forget to save the model at the end of training. Finally, we evaluate the model and repeat the process because getting it right on the first try is difficult. Now let's talk about data loaders. As I mentioned earlier, they are used in both training and evaluation, and we can set them up in two ways. The first method selects a random batch of data in each iteration, while the second method processes all batches in one iteration. Let's compare these two methods with an example. Suppose that we have 4,000 batches in our training set, and each batch contains 64 samples. And let's say that we train for 1,000 iterations. If processing one batch takes about 30 seconds, we can calculate the training time. In the first method, we will take 1,000, multiply it by 1 because we have just one random sample that we selected, and we multiply that by the time it takes to process that batch. This will give us 8.33 hours. In the second method, we will multiply that by 4,000 because we want to process all batches in each iteration. If you do this, then you will get 1,388 days. You see, this is why I showed you both methods, because you need to find a balance so that training does not take forever. The second method is the ideal method because it ensures all training data is used, but it is not practical. I mean, you need to have a very powerful computer to be able to process all that amount of data. The first method is faster, but might not use all data evenly. Some batches will be favored even though we are using random. Some batches are not going to be used. So you need to find a balance. Let's talk about the training loop. You should adjust parameters like model size and batch size to make the best use of your GPU memory. Ideally, GPU usage should be around 90% or more, but not too close to 99% to avoid running out of memory. Here, for example, I have 8 gigabytes on my VRAM. So if I could fill 7.5 gigabytes, that would be great. How do you figure out the optimal batch size that your GPU can handle? Well, it's easy. First, start with a small batch size. If the GPU can handle it, then stop the training and increase the batch size. Keep increasing it until you find the highest batch size your GPU can handle. Also, remember to save the model regularly and monitor the loss. Tracking the loss is very important because it shows whether the model is underfitting, overfitting, or training well. Here in the first graph, we see that the model is underfitting because the loss was not improving and it stagnated, while on the far right, the model is overfitting because the validation loss is increasing. So the ideal situation will be this one. The training loss should decrease over time and the gap between training and validation loss should stay small. After training, test the model by generating text and evaluating the response. If you are not happy with the results, don't worry. Just repeat the process and adjust different settings. This is how deep learning works. It's rare to get perfect results on the first try. You have a lot of hyperparameters that you can adjust, so just repeat the training process until you find satisfying results. During evaluation, check if the model can produce clear and meaningful text. This is the important thing. If the model can produce coherent text, then you are good to go. The model does not need to be perfect at this stage because this is just the pre-training step. The goal here is to make sure the model understands the language you are training it on. Later, we will fine-tune it to make it more useful. Ready? Let's start coding. Before showing you the code, I want you to go to my GitHub repository and pull the latest changes because, as I said before, I am regularly updating the repository. Whenever I make a video, I try to push the notebook and the slides. So please pull the latest changes so that you get these two notebooks. So open notebook for one model training all batches. Both of them are similar. There is just a change in how the data loader works. So let's look at the first one. Here we are loading the tokenizer. Let me run this. We have seen this before, so let's go fast. Here, make sure that that you train the tokenizer. Here we are loading it. We have the get vocab size to basically give us the size of the vocabulary. And now we are going to create the model. Here I did something else. I have created a script. Inside transformer, we have the model. Basically, instead of putting this in the notebook, I made sure to put it in a script so that we can load it easily. And here we are going to give the GPT language model constructor some variables that it can use when instantiating the model. And this is exactly what we did. So you can see that I imported the GPT language model class from the model scripts. And here are the hyperparameters that I am using. Here I am just showing you the notebook that will train the model. You will see later in the video that I'll make a lot of tries. So I'll change these values regularly. So after creating the model, I am passing it to the device, and this is going to be computed automatically by Torch. So if you have a GPU, we will use CUDA. If you don't have it, then this will fall to use a GPU. So let's run this. And here it shows me that I have a very small model just for demonstration purposes. After creating the model, here comes the data preparation. Let's load the combined text. Remember, we will load this sequence of text and we will use the tokenizer to embed it. And this will give us the number of tokens that we have in the data. So let's wait for this to complete and then I will come back. I am back, and as you can see, we have 618,000 tokens in our dataset. Now let's split it into training and validation splits. Here first we are converting the encoded text sequence into a tensor of numbers. So if you want to have 95% of the data as training, then put 0.95. If you want to keep it like this, keep it like this. And here we are splitting the data into training and validation. Let me run this. And here comes the data loader. Here we are using all batches. So here we have this text dataset. We are giving it the data and the block size. The block size controls the maximum input that the large language model can accept. If you set block size to 256, then that means that you cannot feed an input with more than 256 tokens. That will fill the context window and you'll not be able to compute the answer. So make sure that the input stays below or equal this value. Here get item, we will give it an index and it will give us the two pairs, X and Y. And here we will just give it an index and it will add the block size so that I get the input X and I'll predict the next token in the sequence. So this is what get item does. And we are going to use this text dataset inside the get data loaders method. And this one will give us both the training loader and the validation data loader. So let's see how this works. Here we are creating two instances of the text dataset class, and here we are giving it the training data as well as the block size. And here you can see that we are moving the tensors to the device. After getting the training dataset, we can create the data loaders. You give it the dataset, the batch size, and shuffle. Make sure that shuffle is equal to true so that we randomize the data. We are doing this just for the training because this will be used to optimize the model, whereas in the validation data loader, this is set to false because we are not going to use the validation data loader or the validation data to optimize the model. We are using this just for evaluation purposes. So run this, and here we can test this just to make sure that it is working. So we are getting the training and validation data loaders from the get data loaders method, and we are using the next method to basically get a batch. And after printing the shape, here the batch size is 128, while the block size is 512. So let me run this. Okay, so it is working, great. We arrived at training. So here, first we want to estimate the loss. This is going to be used in order to plot those loss curves that we have seen in the slides. So first, put the model in evaluation mode because we are not going to compute gradients. Then for each split, so we are going to do this for both training and validation, we are going to compute the loss. And here, because we have, so here we need to evaluate this integer that I called evaluation iterations. Why? Because we don't want to go through all the data, through all the batches that we have in the validation set, because this will slow the training process. We just want to get a sample from the validation data and run the model on it and get the loss value. So what you could do, if you want to have the validation be computed on all batches in the validation data, then remove this and calculate the loss on all batches. But if you want the training to be a bit faster, then add this value and provide it to the estimate loss method. So we are calculating the loss for each batch, and after that we are calculating the mean. Finally, before leaving, make sure to set the model to train because we are going to resume training. And finally, we return the loss that we put in the output dictionary. So make sure to run this cell. Here, save checkpoint. So this is very important because let's say that you are training the model for 10,000 iterations and something malfunctioned and the training stopped for some reason. So at least you have saved the model multiple times during training. So don't wait until the last iteration to save the model. No, make sure to save it regularly during the training process. And here, basically, we are using the save method from Torch to save the checkpoint. Here we are saving multiple things. So we are saving the epoch, the state dictionary. This is very important for both the model and the optimizer, and the last value for the loss. So run this. And now here comes the training loop. So as you can see, I already done this, but let's see how it looks like. First, we have some parameters that we can tweak. The number of iterations. This is the epoch, so I have called it iterations. Evaluation interval. So this means for every 10 epochs, we are going to use the estimate loss function to compute the value. This is what we are getting here. So you can see that in the first iteration, we computed the loss. After 10 iterations, we are evaluating the model, and so on. So this is what eval interval is used for. Eval iteration, as I told you, it's going to be used by this one, basically to limit the number of batches that are going to be used to calculate the loss. But if you don't want to use this, then remove it from the estimate loss function entirely. The learning rate will be used by the optimizer, and here we are using Adam. Finally, we are getting the training and validation loss again, data loaders again. Here we have two arrays to keep track of the loss during training so that we can plot it down below. And now we start. So for each iteration and for each batch in the training data, because this one is all batches, so we need to use all batches in the data in each iteration. And this takes a lot of time to complete. First here, this one is just for evaluation, but let me collapse this and start with the training. So you give the model the X and the target. It will give you the losses, basically the probabilities. Here you compute the gradients and perform the optimization. After that, in this block, we are going to evaluate the model. So if this condition is valid, we are going to use the estimate loss function and we are going to append the loss for training and validation in these two lists. And we have this print statement just to print this so that we can see the values while the model is training, and to intervene. If we see that the validation loss is starting to go up, it should be safe to stop the training because the model is degrading, it's not improving. And finally, we save the model after each iteration. So if I close this, you can see that when I finish working on all the training batches, I will save the model. After training, I have this so that I can plot both training and validation loss. And as you can see, the model was doing good, but I stopped it because I was just creating the notebook. But this is what you should see when training the model. Both train and validation loss should go down over time, and the gap between them should be minimal. Finally, here, if you want to test your model, you can basically give it an input and use evaluation again. We don't want to compute gradients, and use the generate method. And finally, decode tokens so that you get the text back. So this is similar to what we have here, but if I scroll down to the data loader section, you can see that it is very simple. You are just going to get a split. So do you want to get the training split or the validation split? And we are going to use that to get the data. And finally, we are going to basically get a random index with source.random integer and get x and y and use that in the training loop. So if I scroll down to the training, you can see that the estimate loss is the same, save checkpoint is the same, but here you can see that, let me collapse this. This time we are iterating just over the max iterations. There is no need to iterate over the data loader because we are getting random batches each time. So here we use the getBatch method, and because we are training the model, we will use the training split, and this gives us xbatch and ybatch, but randomly. So here, this one is faster, but you will run into issues because sometimes some batches are not going to be used in the training because this is a random process. So you need to increase the number of max iterations so that you make sure that the random process will use all the batches. So basically, this is the only difference between the first and the second notebook, but the rest stayed the same. So here we plot the losses and we generate from the model. So this is what I wanted to show you in the first part. In the second one, I will start training, I'll start playing with these hyperparameters and see if the model will learn the Darija language, and hopefully it does. And then if this works, and I will show you that this is not very easy to get the model to work from the first try, but I'll show you how to follow the process that I showed you in the slides to get good results. So I started training the model. I kept the first hyperparameters like this. So that gave me a model that contains 0.5 million parameters. This is very small, and I think the model will underfit, but let's see. So I kept these things the same, and when I came to training, you see that the model was doing good. So the loss started at around 6.9, and at the end, it reached 4.7. And the gap between the training and validation loss was very small. So here we have 4.7, and here we have 4.9. So 0.2 difference. It's not that big. And if we plot the training and validation loss, you can see that the loss was decreasing steadily, but you can see that it's stagnated and it will not go down. And this is very similar to the plots that I showed you in the slides. And this shows that the model is underfitting. And we were expecting this because the model is very small. We have a lot of data. So the model is not able to learn more. What we should see, if we increase the model, this should decrease. So the loss should decrease maybe to around here. It will also stagnate. After that, we will increase the model size even further and see when the model will overfit. So at a certain point, the model will be so big because we have a small data set, the model will overfit that data. Let me do another run. This time I will change the hyperparameters to increase the size of the model, and I'll come back. And I forgot to say that I am using the random batches approach because this one is faster to train the model. But later I'll go back to the all batches method and try it out also. And before I finish this part, I also want to say that when I generated some tokens from the model, I see that it isn't good. And this matches what we see in the training loss. the model didn't learn a lot from the data. This is why the generation isn't that great. Here are the results from the second training run. And as you can see, again, the model was underfitting. If I put this here and the first run here, you can see that they are similar, but here the loss was lower, but you can see that the loss stagnated. So that means that the model did not improve a lot from what we did before. Also, the generation wasn't that great. And here the model is 3 times bigger. So here we have 1.5 million parameters, but because the number of players is just 1, that means that we don't have a lot of parameters. So the model will not be able to learn a lot. So what I will do now, I will increase this to, let's say 3. Let me see how this will give me 3 million parameters. So let's increase that to 4. And also something very important is the embedding. If I'll change that to 768. This will increase the size of the model a lot. Why? Because we are going to, so this means that each token will be represented by a vector of size 768. If the vector is big, this means that we will store a lot of information for each token. And this is why the size of the model jumped a lot to 30 million. So now let me see. So I'll also decrease the batch size because the model will take a lot of memory if I try to load it on my GPU. So let's just do this. Let's keep this to, let's use 30 million. Here we have 4 layers, the number of head. So this will not change the parameter size. So you can see that it does not change. It will just have multiple heads. The block size controls the max input dropout. This one is used for overfitting. So I'll just decrease this to 512. So this will give me 30 million. And then I just want to go progressively just to see if the loss will go down. And if the model still doesn't have a lot of parameters to learn more, then I'll keep increasing the embedding size. So I'll keep this. I also want to show you that the checkpoints are here. So make sure to create folders inside the output folder so that the checkpoints are saved correctly. So this is great. I'll just duplicate this because I want to keep those graphs just to show you at the end how those parameters affect the model training. So let's call this 3. Here I have block size 512. I think these are enough. So now I'll just go back to this one. Let me show you what I have here in Ghosty. You can see that the model was taking 6 gigabytes before. So I'll just free the memory, restart the notebook. As you can see, now we freed the memory. Here I am using OBS to record. This is why I am using a little bit of memory. Let me close these because I no longer need them. And here, so I'll keep these parameters. I will go down to the training loop and I want to change some things. So here I will change the learning rate to 3e-4. I want to increase it a little bit. I want to keep the max iterations to 1000. And here I need to make sure to change the folder to run number 3. This is the third run. I forgot to save the second run, but that doesn't matter because the model was not great. So let me create the new folder and everything should work. So I'll train the model and I'll come back. I have finished the third training run. Here is how the training and validation loss functions looks like. I have copied both images from this run and the previous one, and I have them here in Inkscape just to see the difference. You can see that both of them started at a loss of 7, but then you can see that here we quickly reached 4.9. In the previous run, that took us 40 evaluation steps, so that took us a lot of time. So with this big model, we were able to decrease the loss quickly, but after that, the loss stagnated again. What I will do now, because increasing the size of the model did not help, so I'll stop using the random batches approach and use the all batches approach. This one will take a lot of time, but what I will do, instead of having 100 iterations, I'll just keep 1 iteration, and here I'll loop over all the batches, and hopefully this one will work. So I will name this run number 4. Let me go back, or first let me go to the previous notebook. I need to free the memory. So let's click on restart. I'll close this. I'll go to the top, and here let me change some values. So I'll keep the batch size small. I'll use 32. Here the block size, let's make this small to 56. The embedding size, I'll use 512. for now. Let's increase the number of layers to 6. Let's see what this will give us. So this gives us 20 million. This is big. So I'll decrease the number of heads to 6. Oh, that's increased the value. I don't want to decrease the number of embedding or the embedding size, because if I decrease this, yes, the model size will decrease quickly, but I want to have a sort of big embedding vector for each token. So let's keep this as 512. I'll keep this to 6 layers. And here I have to decrease the batch size to, I think, 16 or 24. So let's try 16 first and see if this will fit. So currently we have 20 million parameters, or actually let's try something. I'll decrease the number of layers to 4. I'll keep the batch size 32. We have 13 million parameters. This is exactly what we had before. And now let's train this just to see if the loss will decrease or not, because it stayed at 4.7. So I would like to see the loss keep going down, because this is underfitting. It's not, the model is not learning from the data. And my assumption is that by using random batches, that did not help our model. So let's give the model all the batches and see if that will help it generalize better. So I'll run this training run and I'll come back with the new results. This is the 4th run, I guess. I have finished training the model for the 4th time. And as I said, this time I used all batches. This method is really awesome. And I think it's the one that we should use from now on. Why? Because let me show you. So the model stayed the same. This is the size, it's 13 million parameters. We encoded the data. Here is the data loader. So this time during training, we were iterating over all, where it is, here it is. We were iterating over all the batches in the training loader. And as you can see, because I have a lot of data, here I have 8,700 steps almost, and the training loss was doing good. Let me show you the graph, it looks interesting. If you remember, in the slides I showed you that if you see this means that the model was overfitting. But this is exactly what we need. I mean, you will be confused right now. Why are you saying this? Let me explain. First, the loss that you see here was not computed over all batches in the training dataset or in the validation dataset. Remember, if I go back to estimate loss, you see that we have this variable that controls how many samples that we take from the data loaders. If you want to get the accurate loss value, you should remove this. I said that this will increase the training time, but this will give you the actual values. I kept this just so that I don't slow down the training. But if you estimate the loss every 100 epochs, that will not cause a lot of problem. So it's safe to remove these if you want. Also, let me go back to the training, to the graph. You can see that here, let's say that evaluation iteration, that variable was 200. And I have more than 8,000 batches. And you can see that I have just one iteration. I intentionally set max iteration to be 1. And I just went over all the training samples and optimized the model. So those 200 samples, the model has seen them just once. So it did not overfit on those samples. So you can see that the training loss went down, but it doesn't mean that the model saw those 200 samples more than once. It has only seen them once. And this is promising. It's really awesome. Here, the validation loss was going up. Why? Because let me go back to how we split the data. So you can see that here we used the index. So whatever comes after this, we will take it as a validation data. Here comes the problem. My model is not a model like ChatGPT or Gemini or the other general models. So those are trained on the whole internet and they are expected to know everything because those are general models. So if you have, for example, coding samples in the training set, you should have coding samples in the validation set. But my model is simple. It is trained just to learn the Darija language, but specifically to mimic me or another person. So here, my dataset contains conversations between me and other people. We could have in the validation set conversations between people that are not split between the training and validation set. So this is why what we might see in the, let's say that during training, I was talking with people about let's say programming, computer science. But in the validation set, I was speaking with people about, let's say, football and something else that is not related to the training set. The model will not be able to generalize. Why? Because in the training set, we have just samples that are related to programming and computer science. So this is intentional. So I wanted the model to be able to learn from the data as much as possible and to be able to model the Darija language. I will also experiment with removing the validation dataset and keep one data, give it to the model, and see at the end if it is able to learn the Darija language. And let's go and see the generation. So here, excuse me if you don't know the Darija language, but those that understand it, people from Morocco or Algeria, will see that the model is generating good text. So here, let me see. So this is the input sequence. You can see that it is here, and after that, these are tokens that the model generated. You can see that it generates emojis. This is how we laugh if we speak with other people. We keep pressing H. It's funny, I know. What else? So let's see. I'll change this. To say hello, we say salam, salam labas. So this means hello, how are you? And let me see what the model did generate. So salam labas alik. Hello, how are you? Hello, Ahmed. So as I said, people from Morocco or Algeria would understand the text. It is not perfect, but the model is using, I'll say, correct words. It's not using just, random words like it was before. Actually, let me go and open the notebooks that we started with. This is the first try. If I go to the generation, so this is the text that we got. It's completely nonsense. So for those that understand the Darija language, we'll see the difference. Let me put them side by side just to see. So here is the before and here is the after. It actually worked. So this is why I said that if you see this, it does not matter. In the slides, I showed you that this is bad behavior because the model will not generalize. And this is true if you are training classifiers, those classical models. But with LLMs, you want the model to learn as much as possible. Because don't forget, this is just a base model. Here is just completing the text. The conversation is not meaningful. It's not coherent. But don't forget that we have a fine-tuning step. We will take this model and fine-tune it on a conversational data so that the model is able to mimic me or other person. I'm really excited, and in the next episode, I will show you how to form that dataset, and after that, we will start fine-tuning the model. See you next time.